And so this is the example we'd like to work through with you right now. This corresponds to a worked example in Harris section 6.4, where I show you how to use beta values to calculate the concentration of any lead-containing species in a saturated solution of lead 2 iodide containing dissolved iodide with a known concentration. And so what we're given is, we are given the concentration of the iodide in solution, 0.0010 molar. We're told that the solution is saturated with PbI2, and the key here is that allows us to use the KSP to find the original lead 2 plus concentration. And then by being given the K values and the beta values for every subsequent complex ion formation, we can use the K expressions and the beta expressions to determine the concentration of lead and the lead iodide complex species in the solution. So our first step in solving for the concentrations of all these lead-containing species is we need to write equilibrium constant expressions to describe every equilibrium. For the KSP would be the concentration of lead 2 plus times the concentration of iodide squared. For K1, the formation of PbI plus, the equilibrium constant expression would be PbI plus concentration divided by the concentration of lead 2 plus times concentration of I minus, products over reactants. And remember, the beta values are just different types of equilibrium constants in terms of their notation, but they're written like every other equilibrium constant. So beta 2 would be concentration of PbI2 aqueous divided by the concentration of Pb2 plus times the concentration of I minus squared. Beta 3 would be the concentration of PbI3 minus divided by the concentration of Pb2 plus times the concentration of iodide cubed. Beta 4 would be the concentration of PbI4 2 minus divided by the concentration of Pb2 plus times the concentration of I minus to the fourth, and this will be our complete list of expressions. We can then set each expression equal to the constant value, and then we can use our initial calculation of the lead 2 plus concentration in the system to calculate the molar concentration of all the other lead-containing species in the system. And so this is the power of the beta values, is if we have a complete list of our related equilibria, we can use the KSP to solve for the Pb2 plus, and we'll know the I minus concentration because it's given to us under the statement of conditions. So then we can use all of these other equilibrium constants directly to calculate the concentration of any of the other lead iodide complexes or complex ions. And the reason that we can do this is because the equilibria are related, the concentration of lead that satisfies any individual equilibrium constant expression must satisfy the concentration of lead in all of the equilibrium constant expressions. There can only be one concentration of lead for all of these related equilibria if they're describing the same system. So our problem-solving strategy is to first use the KSP to find the lead 2 plus, and then we'll know both the lead 2 plus concentration and the iodide concentration, and we'll be able to calculate the concentration of all the other lead iodide complexes in solution. From the KSP expression, we can write that 7.9 times 10 to the negative ninth is equal to the concentration of Pb2 plus times I minus squared. For this calculation, we don't need an ICE table because we are told what the equilibrium concentration, we are told what the iodide concentration is in our solution, and therefore, similar to a common ion effect problem, we can just plug in the value of iodide for the concentration. We can just plug in the given concentration of iodide for the concentration of I minus, and we'll solve for the lead 2 plus concentration. So our KSP 7.9 times 10 to the negative ninth is equal to X, where X is the lead 2 plus concentration, times 0.0010 squared. Rearranging and solving for X, we find that the lead concentration for our system is 7.9 times 10 to the negative third molar. And now we know both the lead concentration and the iodide concentration that must satisfy all these equilibria just by evaluating the KSP. However, more importantly, by knowing these two concentrations, we're now in a position to easily evaluate the other equilibrium constant expressions, both the Ks and the betas, to determine the concentration of the other lead-containing species in the solution. So for instance, we can rearrange the K1 expression and solve for PBI plus. The bottom tail of the I went away, so please fill that in. That missed that in my handwriting. The concentration of PBI plus can be solved by taking the denominator of the equilibrium constant expression, multiplying both sides by the lead-2 concentration times the iodide concentration. So the PBI plus concentration is equal to K1 times the concentration of lead-2 plus times the concentration of iodide. It's equal to 1 times 10 to the second times 7.9 times 10 to the negative third times 1.0 times 10 to the negative third. And that gives us a PBI plus concentration of 0.00079 molar. We can do the same process with the beta 2 expression to find the concentration of soluble lead-2 iodide. PBI2 aqueous is equal to beta 2 times concentration of lead times concentration of iodide. And once again, from the KSP, we got this concentration and that concentration, and we know the value of beta 2. So the concentration of lead-2 iodide aqueous can be found as 1.4 times 10 to the third times 7.9 times 10 to the negative third times 1.0 times 10 to the negative third squared, giving us a PBI2 aqueous concentration of 1.1 times 10 to the negative fifth molar. We can repeat this process with beta 3 and beta 4 to find the concentration of PBI3 minus and the concentration of PBI4 2 minus. If we do that for beta 3, the concentration of PBI3 minus is equal to 8.3 times 10 to the third times 7.9 times 10 to the negative third times 1.0 times 10 to the negative third cubed, or 6.6 times 10 to the negative eighth molar. And we can do the same again for PBI4 2 minus, which gives us a concentration of 2.37 times 10 to the negative 10th molar for PBI4 2 minus. And so just by remembering that all these equilibria must be related and having access to the beta values that describe the formation of the complex lead iodide species and complex ion lead iodide species, we can quickly and easily use the KSP to evaluate the concentration of every lead iodide species in solution. Big picture though, what I wanted you to take away from this conceptually, chemistry-wise, is a reminder that when we evaluate a KSP, the KSP is only part of the whole equilibrium picture that describes an ionic compound's solubility in water. You also need to consider the possibility. You also need to consider the potential for the formation of these complex ions between the Lewis acid and the Lewis base, because through Le Chatelier's principle, they also govern the solubility and the speciation of the metal cation that's part of that precipitate. In general, for most of you, unless you've had inorganic chemistry already, most of us in this class will not have the background needed to predict what complex ions might form. So in class situations or lab situations where we want you to consider the formation of complex species or complex ions as part of an equilibria, we'll tell a series of equilibria. We will give you the parameters and tell you what species you should consider the formation of and give you the beta values you need to determine their concentrations. So take some time, get a little practice with this skill. I think you'll find this one pretty straightforward. And up next, we're going to have an introduction to the systematic treatment of equilibrium, where we're going to use this type of thinking to get even deeper into equilibria problems and show you how to make more quantitatively accurate determinations of various chemical concentrations in solution at equilibrium. I'll see you there in a minute.